do in 1 week from today. That still is the data analysis setup piece, which includes hopefully the research question you're planning on going after, the data source you're planning on using, some semblance of a conceptual framework to generate acceptable hypotheses, a brief literature review, and some sense of what you're hoping to contribute to the literature, if anything. And then 2 weeks from today is on the research proposal side is the one-pager. You by yourself are going to tell me something about the research question you're planning on writing a proposal about, and some idea of data set sources you're planning on using. Any questions on these before we move on? All right. So today, finally, even though it's called Difference and Differences 2, we'll finally get to Difference and Differences 1, keeping with my promise to be behind by one lecture at all times. But first I want to spend a little bit, one of you on Thursday asked about testing for balance in propensity score analysis. So I want to show you a little bit about that, give you some idea of what it is and how you might do it with this data. So there are 2 steps in testing for balance in the propensity score analysis. The first step here, kind of prior to, is the diagnosis step, to try to figure out how bad the imbalance is in your covariates. So the idea here is you're just comparing the means of each covariate across the levels of the treatment variable prior to the propensity score adjustment. So usually the treatment variable's got 2 values, 0 and 1, and so you want to generate the means by the treatment level. Here's one way to do it, or a variety of ways. So tab stat will actually take a variable list, which is a list of names of variables. Then you can ask for the statistics. Specifically, you want the mean, and you want it by the treatment variable, so whatever that's called. I've tried to put these in italics to indicate where you're supposed to put in your own variables, and the rest of it is standard data syntax. The next part of that then is to test for statistical differences across the treatment variable. So are the means of a covariate equal across the 2 groups? You can do this by t-test, so you say t-test bar name, comma, by treatment variable name. So this says, okay, like test morbidity count by whether or not you got struggling extent. Same thing, you can do it with an ANOVA. An ANOVA will give you the dependent variable is the variable name, the thing that you're testing the means of, and then by the level of the treatment variable. And then a standard practice in the propensity score literature is to report the standard difference in percentage terms between the means across the two arms, the treatment and the control. And so the formula for that looks more complicated maybe than it is, but you need, for each variable, you need, for each level of the treatment variable, you need the mean of the covariate and its variance, which you can get from Summarize or other table statistics. And so basically the formula is just simply the difference of the means divided by the square root of the average of the variances. Variance, of course, is standard deviation squared, so if you got a standard deviation, you can plug that in as well. But it's not super complicated. It's a good idea. That gives you some sense in a standardized format to say across your variables which are the ones that are least balanced or farthest away from each other. Those will be the ones that have the largest percentage difference in percentage terms. And it also might give you some sense of, even though the differences are significant, they're only, because you have a large sample, they're really small, but they're significant, so I'm not going to worry about them too much, as part of the rhetoric of propensity scores as well. All right, so then that's the setup, and that's kind of, regardless of what type of propensity score analysis you're going to be conducting, matching, stratification, whatever. And then once you've actually done the propensity score, you want to test for balance post hoc and see if whatever application of your propensity score you're using actually is successful in balancing your covariates of interest. So for the matching adjustment, that is where we go through and take each observation in the treatment group and match it 1-to-1 or 1-to-something in the treatment group. You then just repeat step 1 all over again. That is, you go back through and you now compare the means of the covariate across levels of the treatment variable after the propensity score adjustment. The difference here being that you shave down the sample, and so you arguably, hopefully, you'll see empirically whether or not your propensity score was successful in balancing.
How did you shake down to?
So I didn't show you, well, I showed you on Thursday how you did it in the, I mean, I'm presuming we'll go back to Thursday and say, to do the match, you're going to take each one and go one by one, and then this is what you do after you've done the match. Just repeat that.
So that's just like manually going through and like, or is there a program that you can like actually get them to match?
Oh yeah, so I showed you some, I mean, I didn't do one here in class, but if you go to, there's a program called PS Match. That will do it for you. You could do it manually, I suppose, but PS Match has got more options than I care to comprehend at this point. You know, if you have any questions about that, if you want me to show you a propensity score, I can see if I can gin one up for a future lecture. But I mean, the idea is you have it, you did it. That's just for a matching one. For a stratification type application, you want something slightly different. Here you want to basically just test whether the main effect of the treatment variable on the var name and before and after the quintile are the same. So you can do this with, say, ANOVA again. Here, the syntax is ANOVA var name treatment variable and a double pound, then whatever your stratification variable is, the name of your, and so the name of your propensity score quintile variable. The double pound is stated as shorthand syntax for saying, put into this model or expand here a main effect for treatment variable, a main effect for the stratification variable, and their interaction. I'll show you an example in a second. One thing key to note, in prior lectures I've sung the praises of the I.var name called factor variable syntax in Stata. It's really nice because it turns a categorical variable into a set of dummy variables on the fly. That's great for a regression analysis where you specify a model specification. But when you're actually doing, like when you're taking something like I.var name won't work as a dependent variable because you're actually talking about substituting var name with, say, it's got 6 categories. You're talking about substituting with 5 variables, so you can't have 5 dependent variables. What you really want is each dummy variable that corresponds one by one to the categories of that var name. So just letting you know that if you try and do that syntax where you include I.var name as a dependent variable, it will break down. Stata says you can't do that. That's why. So here's unfortunately in that case you might need to actually create manually dummy variables from your main sort of mother categorical variable. So here's a stratification balance example. It's just a sequence of, I'm just showing you a sequence of ANOVAs. So here's the command in Stata, ANOVA, and then I'm using the LXizer comorbidity count. I'm treating it as a continuous variable. It ranges between 0 and, I think theoretically it's about 29, but in reality it's something like 8 or 10. And then the treatment variable here is drug-eluting stent. So what I'm doing here is I'm just trying to get the main effect, the F statistic on the main effect of drug-eluting stent, so how unbalanced these things are. If these things were not significantly different, if the means were not significantly different, then the main effect, the statistical test of their difference would be 0. What we find, in fact, is that the F statistic is over 2,000. The p-value for that main effect is less than 0.001. It's vanishingly small. So then imagine I've done all the logistic regression, generated the propensity score, chopped the propensity score into quintiles, all like I did on Thursday of last week. And now I want to test whether or not my balance was successful. So now I run an ANOVA with a dependent variable still with a comorbidity count, but now the independent variables are drug-eluting stent, double pound, and then the quintile variable. What that gives me in output terms is a main effect for drug-eluting stent, a main effect for the quintile variable, and then their summary of their interaction term in the ANOVA sense. We don't care about these other two. We are controlling for them. What we care about here is whether or not the main effect remains significantly different after accounting for the quintile. What you notice is that the p-value shrank substantially from over 2,000 to 115, but an F statistic of, the F statistic shrank substantially from over 2,000 to 115, which is great, except that 115 is still a pretty huge F statistic. Why is it so big? I have 711,000 observations. So even small differences are going to come back as significantly different. That's why when we do this, the part I didn't actually show an example of, I want to calculate the percentage differences in means across the levels of drug-eluting stents, across whatever our treatment variable is. So we have some sense of both not just the statistical difference, but whether or not quantitatively or situated, like whether we have some sense of how important they are. So this could be, this means could be relatively small, the difference could be relatively small, but still finding a significant difference in this example here. So what would I?
Sorry, when you say significant difference, I mean between like the outcome, which is the comorbidity count, and.
So what I mean is that the outcome is not well balanced. The test of whether or not the outcome differs by whether or not the mean comorbidity differs by whether or not you got a drug-eluting stent or not is significantly different from each other. The two means are not, reject the null that they're equal to each other. So we find that, in favor of the alternative hypothesis that they're significantly different from each other. In other words, they're not balanced. Remember, comorbidity count is something we're trying to control for in our analysis of the effects of drug-eluting stent on other stuff. In other words, the difference in patient comorbidity load is going to influence who gets drug-eluting stent versus not. Now, it may be that the influence is not important. After we balance it, the difference is not important. It's still really small. We may want to go back to what we do about this. We want to go back and revise the specification for our propensity score logistic model specification. Include, maybe in this case, if it's a continuous variable, maybe include the square, interact it with some other variables, potentially see what else is unbalanced, to see if we can, progressively balance, reach a specification in which this F statistic gets low enough that this p-value is not significant anymore. In other words, we've found balance. Ideally, all of our variables are balanced. But in the broader sense, you may have a situation where you've got 40 or 50 or 100 variables in a model, say. It's unlikely, it's statistically unlikely, given that 1 in 20 comparisons are going to be statistically significant by chance, that you're going to find all, you're going to be able to balance all your variables such that the statistical significance is going to be insignificant. The p-value is going to be insignificant for all these comparisons. So that's why, again, having the percentage, being able to express the differences in the means across the two arms in percentage differences is a helpful metric to be able to motivate, say, look, here's my covariates were hugely out of balance before I did the propensity score. Now look, they're all either in balance or the percent differences are so small as to be not important. Thank you very much. Now let me go on with the rest of my analysis. I don't think that the 1% difference that happens to be significant here is really substantively important in explaining the treatment effect of drug-eluting stent on whatever our true outcome really is. Of course, and again, propensity scores only account for the things that you are putting in the model. That's the whole idea with propensity scores. They're not accounting for any unobserved covariates in the model. All right, so any questions about propensity score before I move on to, finally, difference in differences? Okay. So let's rewind a little bit and go back to our cross-sectional design. So imagine we have a simple cross-sectional model. We have an outcome y. It's a linear function of four covariates, x1, x2, x3, x4. And so we're saying that y is equal to an intercept plus the product of each coefficient and its covariate summed across plus some error term. In this case, any coefficient, b sub k, represents the average difference in the outcome y for two observations that are identical except for varying by 1 unit x. So we're saying that holding constant x2, x3, and x4, the effect of b1 is that we're raising, the impact. b1 indicates the impact of changing x1 by 1 unit on the outcome y. And here we're getting our identification because by assumption we're assuming a cross-sectional design. We're getting our identification by what I'll call between effects, between units variation. That is, we're comparing two people. We're using this metric or this approach of regression analysis to control for the things x2, x3, and x4 that we can control for, but we're still comparing across individuals. Anything that's not in the model is not being controlled for. We're assuming it away in a sense. You can see why that might be problematic because there may be things besides x2, x3, and x4 that also influence the outcome y. So here's where we start turning into longitudinal design. And now we'll talk about this in the context today of difference and differences, and Thursday, and then next week as well, we'll be focusing on panel data more generally. But the basic idea here is that suppose now we have data on the same unit of analysis over multiple time periods. So we're observing you now and you again in the future, and we're taking measurements on you in both those cases. So suppose now we have this true model, different from our forget the cross-sectional stuff, just some arbitrary true model, an outcome is a function of two covariates, x1 and x2, and an error term u. We can decompose this error term into two parts. A person time period specific error term, also known sometimes as simply a random shock, and then v sub I indicates person specific time invariant piece of the error term. That is all the things about you that that do not change over time, but are not measured in our regression. Say like hair color, sex, demographics, stuff like that. Well, age is going to change in a predictable way. You can use the fact that you've got multiple observations of the same person over time to address this omitted variables problem and to also improve our identification approach.
Can you go back to?
Yeah, sure.
Sorry, I missed. Can you explain again the over time?
This is the same model as before, right?
Yeah.
Just a simple model of gets the linear regression specification, right? But because we now have multiple observations per person, we can take our nominal error term and we can decompose it into two parts. All I'm saying here is that there are two parts to this model.
So it's like things that change over time is the EIT, and then VI is things that don't change over time.
Exactly. So this is the piece of this is the error term specific to a person time period that reflects things that might change over time for a given person. Also, same thing as saying it's a random shock. This is things that are staying stable about you but are not in the model.
So do you predict those like before you pre-specify what the errors are going to be, or no? That it's just,
well, we don't.
right,
I mean, we still can't observe them.
Do you say like the things that would be predicted to change over time, or no? Like
no, this is
just the error.
Well, even you have.
But I guess if you could predict them, you could put them in your model anyway.
Well, not. I mean, if you can observe them,
right.
We can put them in the model, right? But here we're saying this is everything about you. That's going to be the key point. This is everything about you that's not in the model that's time invariant. Not just some things, everything. Everything. So we can take the simple design here, like a pre-post design. Suppose you're evaluating some treatment, all subjects receive it, and you have data before and after the treatment. Here's what the model looks like on a time period specific basis. You've got the pre-period outcome as a function of a pre-period intercept, basically 0 here because you didn't get the treatment. A set of time invariant patient characteristics by assumption, and then the time/person specific error term. This is the random shock plus these time invariant but unobserved characteristics. In the post period, we've got the same thing. I just substituted post for pre. The post period outcome, the post period intercept. You got the treatment. That's a 1. Patient characteristics. And the time period specific error term, person specific error term, and then the time invariant stuff again. Again, I'm assuming these patient characteristics are time invariant. I'm specifying these V sub I are time invariant as well. We could take the simple difference, subtract pre from post, and then now we can say the change delta, the change in the outcome Y, is a function of the change in the intercept, some treatment, and some change in the error term. What just happened? Whoops, V sub I fell out. Why? Because it's time invariant. You subtract it, it goes away. Patient characteristics that are assumed to be time invariant, but still observable. Time invariant, we subtract them. Subtracting something from itself, you get 0. It falls out. So we get some pre-post design interpretation here. Actually, it turns out that the intercept is going to fall out because everybody in this particular silly example, nobody got the treatment in the pre-period, everybody got the treatment in the post-period. So the treatment and the intercept are going to be perfectly correlated with each other. One of them falls out, it doesn't matter which one. All we're saying here is that the change in the outcome, the change from pre to post represents the treatment effect holding constant, you're getting rid of all those time invariant characteristics. We just subtracted them away. We don't even know what they are. Some of them we can observe, some of them we can't. But anything that is by construction time invariant goes away, and we don't have to worry about omitted variables bias from those characteristics. That is the essential insight into panel data. So if you never come to lecture again, at least appreciate that what you get with longitudinal data is the ability to use each person or each observation as its control, as its own control over time. I say it's implicit, but in fact it turns out to be kind of explicit. Either here. So if you get that, then you should have no problem getting this. And if you get this, I can stop talking now, we can all end early. Now the setup is pre-post, but with an explicit control group. So suppose you're estimating or evaluating a treatment that half your subjects got and half your subjects did not, and you also have data from before and after the setup. I didn't say anything about randomization, random assignment of the treatment, and that's going to be where the big thing falls down. But what we've got here is a quasi-experimental setup. In the economics literature and health services, it's generally referred to as difference of differences. That language is starting to permeate epidemiology a little bit, but whatever you want to call it, and I call it difference of differences, this is what it is. If you could interpret this diagram and tell me what the impact of the treatment is, what the average treatment effect is for the treatment, then we can go home, right? So we have a treatment group. Well, we've got observations on, pre-post. So for those people who got the treatment, their outcome went from 2 to 9, a net effect of +7. Those people in the control had a simultaneous change of from 3 to 7, of +4. So 7 minus 4, 3. The average treatment effect, as estimated from this difference in differences setup, 7 minus 4 is 3. You get that? The rest of it is going to be the same thing in various forms, pictures, hieroglyphics perhaps. I'm not kidding. So what is difference in differences? The straightforward way to estimate quasi-experimental average treatment effect. The quasi part from quasi-experimental means we don't have random assignment of the treatment. I also use the word quasi-randomized to describe a propensity score. They're not the same thing exactly. Quasi-randomized in the context of propensity score just means that if everything's balanced on the observable covariates, we're assuming it's also balanced on the unobservable covariates. Here we're saying we have an experimental design, but the treatment is not randomly assigned. Just be careful when you start putting quasi in front of things. Like kind of like experimental, but not exactly. Kind of like randomized, but not exactly. That's what secondary data analysis is. It's kind of like randomized controlled trials, but not exactly. And so the treatment effect estimated from this design is just simply the difference or change in the outcome associated with the difference or change in a given treatment, netting out any simultaneous variation in the associated control group. So we've got treatment and control, we've got pre and post. 4 pieces of data tell us the average treatment effect. What do you need to be able to do this? Not a whole lot in terms of math skills, but you do need some data. Unlike cross-sectional data, you now need data on both the treatment and control, and you need data covering both a pre-period and a post-period, before and after the whatever treatment or program or policy, whatever it is you're trying to study the effects of. In terms of structure, Lisa.
How do you know how much pre-data are not? Because
You want to jump ahead already?
no, we don't have to.
Okay, but so like what's, say more about what you
I'm
bothering
thinking
you.
about this in terms of work hours. So I'll have like 6 months to a year of post data, and I don't know what's a reasonable amount to compare it to for a difference in difference approach, So I didn't know if there was like some standard that people accept.
Let's table that question, and by the end of class on Thursday, if you don't have a suitable answer, let's bring it back up again.
Awesome.
Because I think that there's, what we're focusing on right here is the simple case where we've got a single pre and a single post type observation. It's the least informative, and yet it's it's kind of like don't ask questions you don't know the answer to. So like if you've only got a single pre and a single post period, you get around, there are lots of things you can't do that would make your inference stronger, but that if they don't work would make your inference weaker. And so, this is the we're constraining ourselves to single pre, single post. We start expanding it, things get not more complicated, but the short answer to preview is that it's not so important how much pre-period data you have as much as that if you can convince your readers that the trends in the pre-period are the same between treatment and control, that's when you're in the best shape, because that's going to be the fundamental identifying assumption here. That everything's the same beforehand. The only thing that happened was lightning strikes, the treatment group got the treatment, the control group did not, and let's see how they deviate from each other. So you can leave now if you want to. So in terms of structure, we could either use pooled cross-section or panel data. Just to remind you, pooled cross-section means we may not have the same observations, same little observations from the pre-period and post-period. What if we're doing something like national random or surveying states level? We're getting state level data, and we want to do surveys every year. We may not survey the same people in each state, but we have data reflecting the distribution in Pennsylvania in the pre-period and the distribution in Pennsylvania in the post-period. Panel data means we actually have the same individual respondents or subjects, whatever they are, hospitals in the pre-period and the post-period, and of course, squares are rectangles, but rectangles aren't exactly squares, and so panel can always be used as pooled cross-section, but why you would want to, I don't know. So how do we actually code this in terms of a regression framework? It's not hard. Again, our regression multiplication is simply an outcome as a function of a linear combination of a main effect for x1, which here I'm calling the time dummy, pre-post, 0 at pre, 1 at post. A treatment group dummy, x2, 0 if control, 1 if treatment, and then x1 times x2 is their interaction term. That is, the product of x1 times x2 is equal to 1 if and only if both x1 and x2 are also equal to 1. The coefficient d in that feeble red color is our estimate of the difference in difference effect, or our difference in difference estimate. So how does this work out visually? Okay, so here I wrote the model specification in terms of A, B, C, and D, where A is the intercept, B is the coefficient main effect on time, C is the main effect on group, D is the interaction term or difference in difference. And then I superimpose these things into our little grid. So what we see here is that when time is 0, group is 0, the expected outcome is 3. That's also, so time is 0, this falls out. If group is 0, this falls out. If their interaction term is going to fall out as well, that's going to map exactly back to our coefficient. When time is 1 in the control group, we're adding now A plus B. That value is 7 this is the data I just superimposed previously. This is example data. There's no guarantee that your results will always be 3 and 7. And so, again, now we have, for group 0, we have time equals 1. So everybody gets the intercept plus 1 times B plus 0 times C plus 0 times D equals A plus B. Same thing for the bottom 2 rows in the control group. I'm sorry, the treatment group. This was the control group. This is the treatment group. In time 0, they get the intercept and they get the group coefficient, but they don't get time because that's 0. They don't get the intercept. And then finally, in the bottom right corner, when both of them are equal to 1, they get the sum of all 4 coefficients. What we're saying is that in the absence of a treatment effect, these are a linear combination of, whatever. It's like I'm going to try and say the same thing. It's pretty apparent, I think, visually. If it's not, I'll do it a few more ways to make it clear. So how do we get the difference of differences? We literally take 2 differences and difference them. Thus the difference in differences. So here we take difference 1. Let's say we want to look at the change from pre to post in the control group is simply A plus B minus A. Gives us the coefficient B. Difference 2 is going to be the treatment group from pre to post. A plus B plus C plus D minus A plus C, 9 minus 2, and you're left with B plus D. So we have the difference here and the difference here, and what are we going to do? we're going to difference them one more time just to make sure, and that's going to give us b plus d minus b gives us that coefficient on the difference effect. That is the difference in differences. If you liked it horizontally, you're going to love it vertically. It works just the same. If you want to work through the math, it's the same thing. So the point is, it doesn't matter which direction you do the differences in, then you're guaranteed to have the same d outcome of the difference in differences calculation. And if you don't get that, then you didn't do your calculation right. So that's reassuring. And one last time in graphs. So here, using the estimates before, A was from our example. It turns out these are the actual expected values or the outcome. So A equals 3. We can solve A plus C equals 2. This is 3, but C is actually minus 1. So you got to add that back in there or subtract it off the top row here. And you can see that everybody gets the intercept. That's this gray-blue color. I think they chose poor colors here. I think I'll call that steel gray. Or steel blue, whatever that is. That one right there is A, everyone gets that, and then you either get, in the main effects, you either get the treatment, the treatment group always gets the treatment offset, the control group, or the post period always gets the post offset, and then only the treatment post gets this extra special purpley.
It's purple.
Is it purple?
Yeah. I love purple, and I'm sorry.
I mean, well, I'll think about it. I'll go back to my Crayola and see what color I can match to. On my screen it's violet, actually. It looks much better on a computer, believe me. Because colors will stand out. Okay, hopefully you get the idea, right? The differences visually, horizontally, vertically, with bar charts, all the same thing. How do we actually take this to the data? So if y is a continuous variable, what should we be using? Well, we could model y directly and use ordinary least squares, that is linear regression. And our interpretation is standard, that is the coefficient d is in the same units as whatever your outcome is. If y is continuous, but you want to look at the percent effect, the effect in percent terms, not percentage points, but percent terms, you can log y, usually we take the natural log, and then the approximate interpretation of the difference in difference estimate is in percent terms, or you can get the exact interpretation of the difference estimate at any coefficient. Anytime you log the dependent variable, you can use a natural log here, where y is suitably continuous. The coefficients are going to be interpreted as you take e to the d, e to the coefficient estimate, subtract 1 and multiply by 100, and that gives you the precise estimate of the precise effect size of the coefficient in percent terms. So a 1 unit increase in x is associated with a d percent change or percent difference in the outcome y. In general, be careful when you start logging your dependent variable. You get into some other issues, but I'm not going to tell you what they are. See me if you want to really use logs, but it does happen more, and again, in the economic side of things than the statisticians and the epidemiologists really don't like straight up logging the dependent variable. But in economics, actually, it makes more sense when you think about sort of proportional responses are part and parcel of economic theory. We don't expect absolute responses necessarily, and so we want to model that. Using logs makes more sense. If y is binary, dichotomous, a dummy variable, we can model probability of y outright and use ordinary least squares. This again is a linear probability model, and our interpretation on d, just like our interpretation on all coefficients, is in percentage point terms. That is, the impact of the policy is associated with a 45 percentage point increase in the use of drug-eluting stents, as different from the 45% increase. Or we can also model the logit of y, use logistic regression, which is what the statisticians and epidemiologists, I think, would generally use. But here's where I would say things get hinky. It all goes back to whether or not you think how interpretable a ratio of odds ratios, which are themselves ratios of odds, are interpretable. And so people well, me, I don't speak for other people, but I don't get it. And so, literally, how would you interpret a ratio of odds ratios? It can't be done. It's beyond me. I would argue for turning things back into whatever the unit was that you're talking about and why. So I would say let's calculate the average marginal effects. But if we're going to do that, we may as well just use linear probability models, because that gives us the average marginal effects outright. It doesn't mean you can't use login and get the average marginal effects for a out of a logistic or equivalent regression. And in fact, I don't know myself, but at least know what it is you're trading off here between, again, this standard trade-off of when y is a dependent variable. You can do it the right way, as the statisticians will tell you, but then be prepared to possibly jump through some hoops in interpreting your, when someone says, what was the impact of the policy, what is the differences in a logistic regression? Well, the impact of the policy was that the odds increased relatively by whatever the odds ratio was. They increased, the effect was positive, and it was a whatever increase in the proportional odds or something or other. Try telling that to a press person. Versus at least you could say like, well, increased use by 25%. Seems much more straightforward to me. But do whatever you
do reviewers comment on that?
Reviewers, it all depends on where you send it and what kind of person you get. If you went to a mainline economics journal with a different diff and did logistic regression and reported things in odds ratios, you'd get mean comments about what the dope you are. And if you go to a medical journal and you use linear probability models, you'll get boos and hisses pretty quickly, potentially. And so you got to work either way to kind of justify who your audience is and what it is. Speak to them in the language they understand. If you go to someplace like Health Affairs, well, they probably don't care. They don't understand it either. Keep it simple. But I think probably the best argument is keep it as simple as possible. It still accommodates all the features that you need to be accommodated, whatever those are. And that's kind of context specific. So how do we interpret, the coefficient? We'd say observations in the treatment group experienced a D, where D is the coefficient on the interaction term, unit or percentage point, relative increase or relative decrease on average. We're not controlling for any other factors yet, but if we were, we would say on average controlling for other x's in the model. So let me show you a difference example of sorts. So this was made up of some work I've done recently on exposure to conflict of interest policies and physicians' rate of prescribing generic drugs. So here we might imagine a setup where we have two groups of physicians. One of them got exposed to a policy on conflict of interest, some policy, I won't even say what it is, doesn't matter. And one group did not. This is the control group down here. This is the treatment group. If you can look at the slide and understand exactly what happened, then everything I'm about to tell you well, you won't even need to listen because it will be so darn obvious. But again, we've got 2 time points and 2 control groups. So 4 data points forms our whole thing, our whole setup here. So we specify this as again, just to be explicit about it, our outcome is some rate of generic prescribing as a function of an intercept, a main effect for time, pre or post, main effect for whether or not they got the policy, and their interaction. And again, this coefficient D on this interaction is going to be our estimate of the difference in differences. And then we can decompose from this simple thing. We can add up what the expected value of y is given what group they're in. So for control docs in time 0, again, time is 0, policy is 0, time times policy is 0. They get the value A. And you can add up from there, A plus B, A plus C, A plus D, plus B, plus C, plus D is the treatment docs in the post period. How does this look? So forget that. So what is it we're actually testing here? In a simple 2x2 diff and diff setup, what we're testing is whether or not these lines are parallel to each other. If they are parallel, then the treatment effect is 0. If they're not parallel, then the treatment effect is different from 0. If you don't believe me, let me try to show you. So for everybody, again, this is the treatment, this is the control group is the lower line, the exposed group or the treatment group is the upper line. What we can do, basically, the game we're playing is we're going to take this control group and we're going to move it up to superimpose the physicians at the same starting point. Suppose they had the same baseline rate of prescribing generics. That's, again, go back to our potential outcomes framework, that's what we're assuming, right? We're assuming that they're identical in the pre-period. So we're going to move them up. In other words, we're going to account for their offset C, which is their pre-period difference in prescribing. So we move them up, and then we now have them superimposed. That's the line that's superimposed now. The difference in the in the control group docs from pre to post is just simply this difference B, right? That's equal to that. So we're moving that up now. So this is where we would expect the treatment docs to be if the policy had no effect, if they were the same as the control docs and nothing happened as a result of the policy. However, we observed that their D units different. In fact, their prescribing rate went up relatively more than the control docs by D units, where D is probably some percentage point difference.
So I think I'm a little confused as to why like the starting point would be different.
Because I collected data and this is what I found. I mean, like I don't like it could be random. Just so we have no reason to think they should be different. In other words, we're imposing the equality assumption on them, but we have to account for the fact that the data are saying in the pre-period, for whatever reason, just sampling noise or coincidence or something that we're not accounting for that we're not going to talk about, they should be different. If they are different, this goes back to your point, Lisa, if they are different, then we can control for it, but we'd like, this design is strongest when we can say, look, prior to the intervention, they were exactly the same. If they weren't exactly the same, we can control for it, but if they were exactly the same, then we don't have to control for it, and we can say, hey, look, there's evidence here in this pre-period trend that everything was great, hunky-dory, until lightning strikes. Some of them get the policy, some of them don't, and then we see the deviation. It gets really messy when you've got a lot of difference in the pre-period. These things are really different in the pre-period, and then you're like, oh, but look, they went up by more. Like, well, but so what? That could have been, that could have been totally, like, what we're not doing here. Like, well, in fact, these guys were, somehow they were actually, this policy was, voluntary, and these docs were already juiced about prescribing generics anyway, really excited about it, and so we'll get into this in a second, but are differences causal? Only if the assumptions are met. What are the assumptions? That in the pre-period, these groups are otherwise identical.
Can you only use this for things that are related to time, or can you use it for other variables? Like, if you were looking at generic prescription rate and you wanted to look at it by race and I don't know, some other variable, does that work or not, because it's not like a time?
So you can interact with any two variables you want to. The difference is generally is like interacting two binary variables, and it has this particular usefulness when you're talking about mimicking an experimental setup where you've got a pre-period and a post-period and you're looking at that time period. But anything, like any of the stupid algebra about, embarrassed to even call it algebra, adding up A's and B's kind of thing, is true regardless of what the coefficients actually mean. And so you could totally use it. In fact, you can kind of put a situation where you're just looking at, you don't have to use it just to evaluate a policy per se, and I'll show you an example of that in a little bit. I don't know if that answers your question exactly, but again, you can do whatever you want to. It makes, the different setup makes sense, makes sense. The language is set up for a policy evaluation, but that doesn't mean you have to use it.
So Werner, Ash, and Polsky did this
Yeah.
pre and post the cabbage.
So I would actually postpone Warner Nash and Polsky till next week, if that's okay, but I mean, not next week, until Thursday, but I told you to read it on, for today. But.
Okay, they did do the difference in differences, and then they looked at its effect on race, right?
Right. So they're looking, it's actually a triple difference,
By
which
race, yeah.
we'll get to on Thursday as well. Yeah.
But this approach doesn't help you control for the fact that different groups may have been exposed to the policy, that there were factors that affected whether different groups were exposed to the policy or not, and that they may affect outcomes. Like did you have the propensity score can help you
Balance things.
Yeah.
Right.
Is there a way to use like propensity score with
You can use this in conjunction with covariate control, either regression or matching or propensity score matching, propensity score stuff as well. They're complementary techniques, and you're right, you're exactly right. They potentially control for different things.
Okay.
But everyone, at least so far, on the fundamental basis that I've been beating the hell out of this drum of like, you get the pre-period, post-period, and the whole slopes. The slopes are equal, there's no policy effect, and away we go. So, as you just said, we can actually, in a regression context, it's easy to add covariates to the model. We don't have to do, we can do it as a propensity score, blah, blah, blah. We can do it as covariate control. So, economists don't use propensity scores that often, so they tend to just say, well, let me throw in a bunch of X's here to control for things that might be varying over time, or that might, be other differences, observable differences in the treatment and control group. The interpretation is the same, which is awfully nice, and then, except that we're saying now everything is conditional on controlling for whatever X's are in the model. No big deal. So you're not testing exactly the same effect because you're not controlling for stuff, but controlling is not it's trivial to add those things to the model. And so I made this reference to pooled versus cross-sectional data. It's important to remember that with pooled cross-section, you may have different observations in the pre and the post. Panel, you have the same people pre and post. I think maybe obviously, and if not, we should talk about it. Controlling for additional covariates is more important in pooled cross-section than it is in panel data, right? Because the people who you're in the pre-post comparison, your time invariant, if they're the same people, all their time invariant stuff didn't change. We can difference it out and move on. And so that's why you might want to be more concerned about changes in the sample composition from pre to post that may occur just by sampling. You estimate a different, we're surveying Pennsylvania pre, we're surveying Pennsylvania post, we get different people, they have different characteristics, those characteristics might influence their outcomes. Let's control for them, and then we can make this problem go away. If there's, to the extent those are time invariant things that we're controlling for, we've already controlled for them in a pooled, in a panel data setup. Another point to point out is that so far everything, the policy has been a binary, did you get the policy or not? It's trivial to modify that to make this a continuous measure of the policy. You might think about a proportion, exposure, how much of the policy did you get? 0%, 20%, 50%. I suppose it could be any kind of continuous variable, but I think usually it's just a binary. Sometimes it's a fraction, and then you don't actually change anything. You're just, the impact now is a function of D represents a 100% change in the policy. You need to scale D if you had a lesser policy, because if you're measuring measuring policy from 0 to 1, D is what? It's the average impact changing, for a 1 unit change in policy. A 1 unit change in policy is 0 to 100%. If the policy if you want to look at the effect of a 50% exposure on outcomes, you divide D by 2 or multiply it by 25. Or the other setup is that you might think about, again, kind of mimicking the randomized controlled trial setup, you might have multiple arms, right? You might want to control, you have some control and you have 2 different intervention groups and you want to compare each of them to a control. The framework can handle that very straightforwardly. So there's still a common time trend. I just didn't have room to write out time, so I just put T, and then each of the intervention groups has its own policy dummy variable, and then they each have their own interactions with time, and we would reflect these, or interpret these as basically parallel but separate, impacts of policy 1 versus the control, policy 2 versus the control. We could then even compare D1 to D2 and say, did policy 2 have a different effect from policy 1 by a simple wall test to say, are these coefficients D1 and D2 equal to each other? And then we could control for whatever else we wanted to in our covariates. So how about a little bit of example with some data and some numbers? Again, going back to my favorite drug-eluting stent. So somewhere in the summer, possibly not until later, did the FDA actually do anything about it? There were safety warnings about the use of drug-eluting stents. Did these have a different, did this policy impact, this policy being the revelation of the safety warnings, did it have a differential effect on primary PCI versus elective PCI for the actual use of drug-eluting stent? Here, it's not so much a treatment and a control. We're just saying there are two groups. People who got primary PCI, people who got elective PCI. Was their response to the policy different? So just to set things up and look at the means, I just did a table. And I want to get the table, so basically it's a 2x2 primary PCI by year. I'm going to subset the data to just if year equals 2006 or 2007, just the 2 years right around, well, this is actually somewhat contaminated because the policy came out during 2006, but the response didn't actually start showing up in data until a little bit later in that year. So this is not the best way maybe to do it, but just for pedagogical reasons, I'm illustrating it that way. Comma, and then contents here stated I want freq, which is a count of the observations in each cell, and then mean of the variable DES, which gives me the mean. So here's the output. So again, this is our kind of treatment and control group, pre and post. We have sample size. Look, a lot more people got elective PCI than got primary PCI. I hope that's accurate. And then this is their use rate in 2006 and 2007 of drug-eluting stents. Went from that.
Sorry.
That's okay.
Treatment is getting the warning?
No. So this is a little bit different, right? The treatment, the time is, the warning came out for everybody.
Right, that's
But the response, the two groups we're comparing now are, did you get elective PCI or did you get primary? Were you eligible?
Oh, to differentially affect elective or, okay, got it.
Elective, so it's a little bit different than just a simple policy intervention that affects one group but not the other group.
Okay.
I'm saying basically, did the policy differentially impact? And the policy is an exposure.
0 is did not get primary PCI, and 1 is did get primary PCI.
Right, and so everybody got a drug got some kind of stent. So this is elective stent use, primary stent use. What? Oh, sorry. So I'm not saying it makes sense clinically. I'm just saying this is the group. But there are two groups of people that we're comparing. People who got elective, not just a drug-eluting stent, some kind of stent. 91% of these people in the elective category got drug-eluting stent in the pre-period. That dropped down to 74% in the post-period. It's a 17-point swing. But among the primary PCI folks, it started off at 86, so 5 percentage points different in the baseline, but dropped by 28 percentage points around the safety warning. So let's put this into a regression context. We're basically taking the same numbers and we're going to test whether or not that difference effect is positive. So we say regress drug-eluting stent on indicated variables per year, and primary PCI, the double pound, gives us the full interaction. So main effect, interaction effect. Again, subsetting just 2006, 2007. Because this is a linear probability model where our outcome is 0, 1, did you get the drug-eluting stent or not? I'm asking for the robust standard errors, and because I got tired of trying to remember what the reference groups were, I asked base levels, which tells data, include the omitted reference in the set so you can remember what it is you're looking at. So here, constant, this is drug-eluting stent use in the elective group in the pre-period, 91.45334%, exactly the same as what we got from the table. We're not adjusting for anything at this point. The treatment control offset in the pre-period is 17 percentage points. The difference between the treatment and control in the pre-period is 5 percentage points, and this is the pre-post, offset from the control group, the elective group, 70 percentage points, 5 percentage points. Diff and diff, a net swing for the primary PCI people of minus 11 percentage points, in English. Primary PCI, drug-eluting stent use among primary PCI recipients dropped by 11 percentage points relative to the drop in drug-eluting stent use among elective PCI users. And we now have a statistical test on that. T-statistic is 17, highly significant.
So if you wanted to, if you had other variables like age and whatever, you could just put those into your model as well at that point?
Oh, that's like you anticipated my next slide. So suppose we control for our usual set of independent variables, just throw them in there. I have, for those of you who don't remember or weren't here, I had a local macro with variables with a list of independent variables. I didn't bother writing it out again. It's got a bunch of crap in it. I just added it to the model, same model specification otherwise, robust baseline. R squared goes up by like 2 percentage points, but our effect estimates change very little, in part because these things seem to be not differentially impacting the use of drug-eluting stents. We're controlling for baseline differences already in the setup. These would be things that would have to differentially affect our estimate kind of in the pre-post sense. And so what we find is that even with control, our diff and diff is still about 11 percentage points. It changes in the third decimal, maybe the fourth decimal by a little bit. From 11,069 to 11,117. Yeah.
Did you tease out STEMI and non-STEMI?
Oh, no. It's just, I don't have that kind of data. But it's a good question, but it's that's what a clinical question.
Yeah, do you think it's relevant to whether or not you use it?
Oh, no, it's totally relevant to the, if this were a real paper, it would be totally relevant, and I'd have to
Oh,
say.
it's not real.
No, well, I mean, these aren't real data, but they're not, the data source is hospital discharge data, which doesn't code STEMI versus non, and so that's where you go, that's the limitation section for these are administrative data. I'll send you my standard administrative data paragraph on they are administrative data, and you're not controlled for blah, 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 blah. Dear editor, please publish my paper anyway. Okay, so now I want to, someone asked about how do we get, I think, well, they didn't ask the question, maybe it was Tori. I can't remember if it was you, Tori, who asked this last time, or maybe it was 2 times ago, about how to get the predictions from a model. So in Stata, the command that you want to do to get those things is margins. Margins takes, so I'm asking here, I want Stata to reassemble the parts of the model to get the the percentage point uses, the levels of drug-eluting stent use for each of the groups. And specifically, I want it for year single pound primary PCI. That's the interaction between year pre-post, 2006, 2007, and primary PCI, yes or no. And so and this is from a linear model, but it would work fine from a logistic regression model as well. It just says, give me this, and I want the actual predicted probabilities here. 91%, 86%, 74%, 58% did that.
Can you remind me of this single versus double pound?
So double pound says put in the main effects as well as the interaction. Single pound says just give me the interaction itself. And so, I didn't show it to you, but this could have easily come from logistic regression. We would have gotten the same numbers. The nice thing is we would have gotten the same numbers in the predicted probability metric rather than some crazy log odds or odds ratio, which I've already admitted many times I simply can't understand. And if you want to take it one step further, you can then type margins plot afterwards, and there's all kinds of options that go with margins plot here. There's a whole book about margins plot. But margins plot just took those 4 numbers, real Purdy-like, and now we have it, now you can see what you're actually looking at. This could be, again, whether or not it's post-logistic regression or whatever. You can see, like, okay, primary PCI is 0. This is the elective, the nominal control group. Their use went down from 91% to 70s, well, mid-70s, right? And then you can see right here, it went down even further. And you can do that whole, we already know how big the net effect, the difference is 11 percentage points, but here's a way to visualize those data if you're into that kind of thing. And I have to say, personally, I've come, in the last year, I've become kind of, not quite, I'm not going to say it's a fetish yet, but really intrigued. Like, I try to do a lot more with the pretty pictures, in part because like it really, like you can convey a lot of information if done well, and it abstracts away from like I've got odds ratios or blah blah blah, like no one wants to look at regression coefficients, they don't have to. And so you can get a lot of mileage, I think, out of pretty pictures. And I think a large part of that has been, in the past, it's just been not possible. So you needed the margins command. The margins command didn't come in to Stata, I think, until 11, maybe version 10. So that's within the last couple of years. You could do this all manually, but it was a giant pain in the ass. And even then, it didn't have the nice margins plot that follows right after it that you could just bang out, hey, take this margin stuff and plot it for me. And then you can, Stata's actually, I don't know if it's as good as R. I've heard R is really good. I think it's better than SAS. But I think Stata's pretty good about letting you either interactively or you can click on the margins plot, and there are all kinds of options you can fill out, but you can also specify them in code and tell it, like, you want to do stuff to the x-axis or the y-axis, or change the title, or these have these little silly little confidence intervals on. You want to get rid of those. You want to make them look like airy. You can do all kinds of stuff. Change the colors. So it's So it's highly useful way to, regardless of the model, that it's a good idea to investigate this further if you want to take your model and display it in a useful way. And the other thing that's nice about it too is that like Stata will pump these graphs. Stata will pump out in, you can pick any variety of formats. You can paste them right into a Word file. You can put them into TIFF, PDF, EMF, WMF, all kinds of different formats. And so it's nice to be able to say when you're writing your program and you're getting ready for the manuscript publication, you have a program where you just basically change something, press a button, and everything gets regenerated. Because there's nothing worse than having to manually type in numbers or try and replicate something in PowerPoint that you're plotting. Okay, I have the output here. I gotta paste it into my little PowerPoint graph, blah blah blah, and then paste that back in. Whereas you keep it all within a single program and. Anyway. Go straight.
Are you okay?
I'm not live, but might not be able to see. That's okay, I only need one eye. So, let's go back to this final question of are difference estimates causal? It's a rhetorical question. Of course, they're not. Nothing is causal in secondary data world. If someone says they are, it would be very suspicious. And challenge them greatly, but because you never know, there might be something out there in the origin. But what is the for them to be causal? We need to, what's the identifying assumption? What needs to be true for these differences results to be causal? We need to have it be the case that the intervention is exogenous. That is, observations are assigned to treatment and control effectively at random, conditional on whatever it is we're controlling for. If that's not true, then we can't be sure that these are causal. It doesn't mean that our difference results aren't better than some other alternative, less well-identified analysis, like something using cross-sectional data perhaps. But what are potentially specific issues that might be lurking out there that we need to think about? Under the category of selection bias. One is this idea that policies in particular are more likely to be adopted in places where they are needed more. So, why would you impose a gun restriction if you don't have a problem with guns? Politically, it might not make any sense. Or maybe it does. Maybe there's kind of a reverse need problem there. It's like you can never pass gun legislation in a place with, a high gun problem because the politics are too radioactive. Whereas in, liberal Maryland or something, it's no problem to impose guns because the Democrats have controlled the legislature there since the dawn of time or whatever. And so it's easy for them to be able to do this. In any event, regardless of what the politics are, we need to be thinking about those kinds of issues with respect to adoption of policy. We're treating them as exogenous, but there may be unobserved variables leading to omitted variables bias in our estimates of the putatively causal effect. So, for example, let's say universal health, this is, I guess, somewhat dated now, in light of tobacco, but universal health insurance legislation is adopted in a state with a high uninsurance rate. How can we distinguish any policy effects from regression to the mean? So they have a high uninsurance rate. I'll talk about regression to the mean in a second and what it means precisely. But how do we know that their adoption of this policy was timed with a drop in uninsurance rates wasn't just, that drop in uninsurance rates wasn't actually attributable to other time-varying factors, like simply regression to the mean or changes in the population. And another threat that might be lurking out, and this is not an exhaustive set of threats, but just some examples of things to think about. What if new legislation in the treatment state pulls individuals from the neighboring control state? So, okay, Maryland passes universal health insurance, and all the those from Virginia, where I was born, not born, where I grew up, migrated over to Maryland. Of course, that would never happen because people from Virginia are not the people from Maryland. But they might do it, and you'd see some increase, or you'd see some impact on, you'd be conflating your estimate of the impact of the policy with the migration, unless you're somehow controlling for it. How could you control for it? Maybe think about something like intent to treat, where if you're able to get information on where they're originally from, say, you could possibly do the intent to treat type of analog to RCT. But these are genuinely potential threats to causal inference on diff and diff. So last, in the waning minutes of the class, just a couple, I realized as I was writing the slides up that I was talking about regression to the mean. I want to make sure people have a good understanding of what regression to the mean is, because it does matter for things like policy evaluation and other methodological things. And I think it's something that is bandied about, like, oh yeah, regression to the mean, but let me try to explain exactly what it is. I think what we mean by regression to the mean. So let's get the setup right first. Suppose we have a fixed sample of individuals, of subjects, and we have multiple measurement situations. So tests, I'm giving you a test. Now, my goal is to evaluate your ability to do something, and I'll give you a test now, and I'll give you a test sometime in the future. Just for argument's sake, let these measurements be distributed standard normal, so they have a nice mean of 0 and a standard deviation of 1. You don't have to have your test metric in a standard normal format, but realize that it's trivial to convert any continuous variable into a standard normal distribution by subtracting the mean and dividing by the standard deviation. And so what we have then is this is my assertion, not a conjecture. What we have is that the expected value of the second test score as a conditional on the first test score's actual realized value, that is x1 equals x, is simply equal to the product of the original test score times the correlation between the two test scores. Correlation ranges between -1 and +1, but unless that correlation is exactly 1, the expected value of the second test score is going to be attenuated, that is closer to the mean, or in this case was standard normal, closer to 0. Either if it started off too low, it's going to be it's going to be closer, attenuated towards the mean. If it's above 0, it's going to be brought down closer towards mean, unless you have a correlation of exactly 1. What does a correlation of exactly 1 mean? It means that you're perfectly measuring performance each time. Whatever it is you're measuring, it's perfect. It's not subject to any random noise. It's perfectly measured. So as soon as you have random noise, you're going to be getting an attenuation. And that is, regression to the mean, finally, is specifically relevant in cases where you're looking at just multiple testing setup in time, and you're conditioning on the initial test score to look at the subsequent test score. So it's not that you say, oh, regression to the mean. Like it has a specific setup, and you have to have this kind of sequence of tests. So let me give you an example where you might have regression, regression to the mean. Let me be a little more clear. So this is some work I'm doing for a while on something else, which is maternal complication rates among physicians. So among obstetricians in particular. And what I did basically is this is years of experience, elapsed years of experience on the x-axis, and their normalized complication rate, that is, 0 is average and positive is bad and negative is good. And this is their annual risk-adjusted complication rates. And so I stratified them into quartiles based on their first year out of residency performance on this metric, and looked at what happened. And you might say, okay, here is an example of regression to the mean. They started off, this is the worst quartile, this is the best quartile. They started off, they kind of meet in the middle somewhere, right? It's not, the question is not whether or not there is regression to the mean. The only question here is to what extent regression to the mean is explaining these differences. by construction, there is going to be regression to the mean because I am stratifying this group based on the results of their first test score, their first performance metric, and I'm watching to see what happens on that same performance metric as they proceed through time. So it's not like, unless there was no error and everyone, like your performance in your first year was perfectly predictive of your performance every other year afterwards, in which case we would expect to see kind of straight lines. The only issue here about regression to the mean is to what extent it's influencing these results. Not that we could measure it by looking at the correlation over time with these test scores. We would, we have a variety of other things going on. But that's my screed on regression to the mean. If you didn't know what it was before, hopefully you know a little bit more about it. All right, I'm done. I will see you guys Thursday. Thursday, we're still open. All right, so, and then in a week, so Thursday we'll talk about Warner, Ash, and Polsky, and talk some more about diff and div. And then Tuesday we'll talk about panel data, and you'll hopefully give me some thoughts on your data analysis setup. Any questions before I get out of here? All right, thanks very much, guys.